For billions of years, the universe has had more than enough time for civilizations to rise, evolve, and take over entire galaxies. And yet when we look out into the stars, we find nothing but silence. No empires, no signals, no trace of anyone who made it that far. So today, we're asking a question that changes everything. Why has no civilization ever crossed the galaxy? And what that answer reveals is far more unsettling than being alone. Now let's begin. Compress the entire 13.8 billion year history of the universe into a single calendar year. January 1st, the Big Bang ignites. March brings the first stars. September, our galaxy takes its spiral shape. October, the Milky Way settles into something resembling what we see today. November, our sun is born from a collapsing cloud of gas and dust. December 21st, the first complex animals appear on Earth. December 30th, the dinosaurs go extinct. And then, in the final seconds of December 31st, all of recorded human history, every fire ever kindled, every empire ever built, every war ever fought, every language ever spoken, agriculture, mathematics, philosophy, steam engines, nuclear physics, space telescopes, all of it, compressed into 11 seconds before midnight. 11 seconds. In those 11 seconds, humanity constructed and collapsed. Roughly 10,000 distinct civilizations developed the ability to split atoms, mapped the human genome, launched probes beyond our solar system, and somewhere in the noise of all, that furious activity began asking a question that has never, I received a satisfying answer. Are we alone? The question sounds philosophical. It is not. It is a physics problem. And the numbers surrounding it are so staggering, so violently counterintuitive, that the moment you genuinely absorb them, every comfortable assumption about our place in the cosmos quietly disintegrates. Start with the basic inventory. The Milky Way contains somewhere between 200 billion and 400 billion stars. The uncertainty in that estimate is itself remarkable. We cannot count our own galaxy's stars with precision because dust clouds scattered across the galactic plane block entire stellar populations from our instruments. But even accepting the conservative lower bound, the scale is difficult to process. If you counted 1 star per second without pause, without sleep, you would need over 6,000 years to finish the count. The Roman Empire rose and fell in less time. Now apply a filter so conservative it borders on pessimistic. Assume that only 0.1% of those stars host a planet with conditions broadly similar to Earth. The right distance from the star liquid water, possible a stable orbit, a reasonably long-lived sun. 0.1% sounds like almost nothing. It is 1 in 1,000. But 1 in 1,000 of 400 billion is 400 million. 400 million potential worlds where something like life might find a foothold. That number alone should make the silence of the universe feel strange. 400 million candidate worlds, and we have not detected a single unambiguous signal from any of them. No confirmed radio transmission, no megastructure blocking a distant star's light in a clearly artificial pattern. No laser pulse coded with prime numbers, nothing. This is the core of what physicist Enrico Fermi reportedly articulated in a 1950 conversation with colleagues at Los Alamos. The logic is disarmingly simple. The universe is approximately 13.8 billion years old. Stars far older than our sun have had time to develop planetary systems, evolve life, produce intelligent species, and give those species billions of years to develop interstellar technology. A civilization that began expanding, even slowly, even at a small fraction of light speed, would have had enough time to touch every corner of the Milky Way multiple times over. The math allows for a civilization to have colonized the entire galaxy, not once, but conservatively, 1,000 times over within the age of the universe. 1,000 times. And yet, silence. Astronomers call this the Fermi paradox, and it is not a casual curiosity. It is one of the most uncomfortable open questions in all of science, because every reasonable solution either implies something deeply disturbing about the fate of intelligent life, or forces a radical revision of how we understand the cosmos. Either civilizations are extraordinarily rare, or they are common but invisible, or something systematically prevents them from persisting long enough to leave a detectable mark on the universe. None of these answers are comforting, All of them demand explanation. The most important thing to understand about the Fermi paradox is what it does not prove. Absence of evidence is not evidence of absence, but only when the absence is genuinely explainable. If someone tells you there is a trumpet player performing on the other side of a thin wall, and you hear nothing that is surprising, if they tell you the trumpet player is performing on the far side of a continent, the silence proves nothing. The Fermi paradox is only a paradox if you assume the galaxy should be loud. Whether that assumption is valid depends entirely on one thing: how far can a signal actually travel, and how long does it take to arrive? The answer to that question does not resolve the paradox. It deepens it in ways that are far more unsettling than the original puzzle. Consider a civilization located 10,000 light-years away, which is not particularly distant by galactic standards, roughly 10% of the galactic diameter. Suppose that civilization has been broadcasting a powerful radio signal continuously for the last 5,000 years. Where is that signal right now? It left its origin 5,000 years ago and has been expanding outward through space at the speed of light ever since. By now it has traveled 5,000 light-years. It still has 5,000 light-years left to travel before it reaches us. It will not arrive for another 5,000 years. The civilization that sent it may have risen, transformed beyond recognition, and vanished entirely before a single watt of their transmission reaches our radio telescopes. The universe is not silent. It is full of messages that have not arrived yet. And that realization that the cosmos operates on timescales that reduce all human urgency to something smaller than a rounding error is where the real discomfort begins. If a civilization 10,000 light-years away has been broadcasting continuously for 5,000 years, that signal is currently halfway through its journey, unreceived, undetected, crossing empty space right now without our knowledge. What does it mean to search for something that may already be in transit, simply not yet here? But before asking why no one has called us, there is a more unsettling question to confront. First, whether we ourselves are capable of calling anyone at all. 299,792 kilometers per second. That is the speed of light through a vacuum. Written out in full, it sounds almost impossibly fast. Light travels from Earth to the Moon in roughly 1.3 seconds. It crosses the distance from Earth to the Sun in approximately 8 minutes and 20 seconds. In a single second, it covers a distance that would take a commercial aircraft more than 30 years to fly. By every standard of human experience, this is incomprehensible speed. And yet, at the scale of the galaxy, it is mercilessly, almost insultingly slow. To feel this properly, consider a comparison stripped of all abstraction. If the Milky Way were shrunk down to the size of the Asian continent, roughly 44 million square kilometers of land, the entire solar system, everything from the Sun to the outermost reaches of the Oort cloud, would occupy a space smaller than a single grain of sand placed somewhere in the time, middle of Siberia. And at that scale, light, the fastest thing the laws of physics permit, would travel at roughly the walking speed of an ant crossing a continent. That is what interstellar communication actually looks like when scaled to something the human brain can process. In 1974, astronomers at the Arecibo Observatory in Puerto Rico transmitted what became the most powerful, deliberate broadcast humanity had ever aimed at the stars. The Arecibo message was a precisely coded binary signal containing information about mathematics, chemistry, the structure of DNA, and the location of Earth within the solar system. It was directed toward a dense cluster of stars called Messier. 13, located 25,000 light-years away. That message is still traveling. It will not arrive for approximately 24,950 years. The civilization that receives it, if any ever does, will be reading a transmission from a species that no longer resembles what we are today in any meaningful way. But even setting aside that extraordinary target, consider something more immediate. As of now, the Arecibo message has been traveling for roughly 50 years. In that time, it has covered approximately 50 light-years of distance. The Milky Way spans 100,000 light-years in diameter. 50 light-years represents 1/2000th of that span. The most powerful deliberate transmission humanity has ever sent into space has not yet traveled far enough to count as a rounding error on a galactic map. And if some civilization within those 50 light-years somehow received it tomorrow and responded instantly, their reply would arrive on Earth around the year 2074. The specific telescope that sent the message was decommissioned in 2020 after a structural collapse. The scientific institutions that approved the transmission have been reorganized multiple times. The political frameworks that authorized it no longer exist in their original form. This is the fundamental nature of interstellar communication that almost every popular discussion glosses over. There is no conversation, there is no exchange, there is no dialogue. What exists is an extremely slow, extremely one-directional dispatch of information across distances so vast that the gap between sending and receiving swallows entire eras of civilizational development. Every message sent into space is not a phone call. It is not even a letter. It is closer to carving words into stone and hoping that whoever finds the ruins can decode what you meant. Humanity has spent decades engaged in what researchers call SETI, the search for extraterrestrial intelligence, scanning the sky for radio signals, letter pulses, or any anomalous transmission that might carry the fingerprint of artificial origin. It is a serious scientific endeavor carried out by serious scientists using sophisticated instruments. But embedded in the entire framework of that search is an assumption so natural it almost never gets examined. The assumption that another civilization would be using communication technologies similar enough to our own that we would recognize their transmissions as intelligent. Radio technology by human standards is relatively mature. We have been using it for roughly 120 years. In the context of the 11-second window that represents all of human history on the cosmic calendar, radio has existed for less than 1 second. An intelligent species that achieved radio communication 100,000 years before us, a blink in geological time, a negligible gap in cosmic time, would likely have developed and abandoned radio technology long before humanity evolved. They would not be broadcasting on wavelengths we are searching. They would be using methods we have not yet invented, possibly methods that require physics we have not yet discovered. This creates a specific and deeply uncomfortable version of the Fermi paradox. We are not merely looking for a signal in a haystack. We are looking for a specific type of signal, in a specific frequency range, in a specific format, recognizable to a civilization that has been using electromagnetic communication for roughly 1 century across a galaxy that is 100,000 light-years wide and has been producing potentially intelligent life for billions of years. The asymmetry between what we are searching for and what might actually be out there is staggering. There is something almost darkly comic about the picture this creates. Humanity spent decades worrying about whether to answer. If extraterrestrials called entire committees, formed protocols, written philosophical debates, conducted about the risks of responding. Meanwhile, physics had already quietly established that interstellar communication does not work like a telephone. It works like dropping a postcard into a cosmic postal system, where delivery takes 10,000 years. The postal service has no tracking feature, and the recipient's address may no longer exist by the time the card arrives. The anxiety about answering the phone was misplaced. There is no phone. There never was. A civilization 1,000 light-years away looking at Earth right now is not seeing our cities, our satellites, our radio towers, or any sign of technological life. The light reaching their telescopes left Earth 1,000 years ago. What exactly are they looking at? And what does that tell us about what we might be missing when we look at them? The answer to that question reveals something far more disturbing than any science fiction scenario has managed to construct. The light leaving Earth right now will take 1,000 years to reach a star system 1,000 light-years away. That is not a metaphor. That is not an approximation. It is a hard physical constraint written into the structure of space-time itself, which means that any civilization with telescopes powerful enough to observe Earth from that distance is not watching the 21st century. They are watching the 11th. They are watching the Crusades. They are watching feudal lords commanding serfs across muddy fields in northern Europe. They are watching hand-copied manuscripts being carried on horseback between monasteries. They are watching humans who have never heard of electricity, who believe disease is caused by imbalanced humours, who measure astronomical distances by naked eye and geometric inference alone. There are no radio transmissions leaving that version of Earth. There are no satellites in orbit. There are no city lights visible from space because there are no cities lit by anything other than fire. From the perspective of an observer, 1,000 light-years away, humanity in its current form does not exist yet. The species they are watching has given no indication whatsoever that it is developing toward technological civilization. They have no reason to point any kind of communication instrument at this small, dim, unremarkable planet orbiting an average star on the edge of a spiral arm. We are to them a world of medieval farmers, invisible in every way that matters for interstellar contact. Now reverse the perspective. When humanity looks outward at the universe today, what are we actually seeing? Every telescope observation is an act of time travel into the past. Light from a star 100 light-years away left that star 100 years ago. The star might have changed dramatically since then. It might have ejected a massive flare, begun the process of expansion into a red giant, or had its planetary system disrupted by a passing stellar neighbor. We would not know for another century. Everything we observe in the night sky is a historical record, not a live feed. The further away an object is, the further back in time we are looking. This asymmetry, where every civilization sees every other civilization as it was, not as it is, creates a communication problem that has nothing to do with technology or intention. It is purely geometric. It is the unavoidable consequence of the finite speed of light operating across distances that dwarf any human frame of reference. Now consider the specific bubble of space within which humanity has announced its existence. The first deliberately powerful radio transmissions from Earth began in the early decades of the 1900s. Commercial broadcasts, military communications, and experimental signals began leaking off the planet in meaningful quantities roughly 120 years ago. At the speed of light, that means the electromagnetic signature of human technology has expanded outward in a sphere approximately 120 light-years in radius. 120 light-years. Within that sphere, there are approximately 15,000 stars. 15,000 sounds like a significant number until it is placed beside the full inventory of the Milky Way. The galaxy contains somewhere between 200 billion and 400 billion stars. 15,000 represents roughly 0.0000004% of the total stellar population. Humanity has effectively introduced itself to an almost immeasurably small fraction of its own neighborhood, let alone the wider galaxy. The image that captures this most accurately is not a beacon lighting up the night, it is a soap bubble. A thin, expanding, fragile sphere of radio waves growing outward at the speed of light through an ocean so vast that the bubble, even after 120 years of expansion, has not yet grown large enough to be considered a rounding error on the galactic scale. The bubble is real. It is expanding. But the ocean dwarfs it by a factor that strains comprehension. And here is the part of this picture that fundamentally reframes the Fermi paradox. Every other civilization in the galaxy, if any exist, is in exactly the same situation. They are each surrounded by their own finite bubble of outgoing signals, expanding at the speed of light from their own home system, covering a sphere whose radius equals however many years their technological civilization has been. Broadcasting. Unless two civilizations happen to be close enough and old enough, and broadcasting long enough that their respective bubbles have physically overlapped, there is no contact possible. Not because either civilization is hiding, not because either is uninterested, simply because the light has not had enough time to cross the gap. This means the question of whether other civilizations exist is almost entirely separate from the question of whether we can detect them. A galaxy containing millions of independently broadcasting civilizations, each surrounded by a signal bubble representing a few hundred or a few thousand years of technological development spread across 100,000 light-years of space, might look from the outside exactly like a galaxy, containing no civilizations at all. The bubbles are simply too small and too sparse to overlap with reliable frequency. The silence is not a cemetery. It may be a waiting room. If every civilization in the galaxy is enclosed within its own finite signal bubble, and contact requires two bubbles to physically overlap in space at the same moment in time, what is the actual probability that any two such bubbles have ever intersected? Given what we know about stellar distances and the likely duration of technological civilizations, calculating that probability produces a number that keeps astronomers genuinely unsettled at night. And it is not evidence of cosmic loneliness. It is evidence of something more systematic, more structural, and in many ways more disturbing than simple absence. In 1961, radio astronomer Frank Drake gathered a small group of scientists at the National Radio Astronomy Observatory in Green Bank, West Virginia, and wrote a sequence of variables on a blackboard. The resulting expression, now universally known as the Drake equation, attempts to estimate how many communicating civilizations might currently exist in the Milky Way by multiplying together a series of factors: the rate of star formation, the fraction of stars with planets, the fraction of those planets capable of supporting life, the fraction where life actually develops, the fraction where intelligence emerges, the fraction that develops detectable technology, and finally, the average duration for which such a civilization remains detectable. Depending on how optimistically or pessimistically each variable is estimated, the equation produces answers ranging from less than 1 to several million. The range itself is instructive. It reveals not so much a calculation as a structured framework for expressing ignorance. The equation is enormously useful as a way of organizing what we do not know. It is far less useful as a way of determining what is actually out there. But the equation's most significant limitation is not its numerical uncertainty. It is a hidden assumption embedded so deeply in its structure that most discussions of it never surface the problem at all. The Drake equation estimates the number of civilizations that are currently detectable. The word detectable is doing enormous and almost entirely unexamined work in that sentence. The equation implicitly assumes that a civilization which exists is also a civilization that we can detect, that existence and detectability are roughly equivalent. This assumption is almost certainly wrong, and the degree to which it is wrong determines everything about how to interpret the equation's output. Consider the following image. Scatter 1,000 candles across the Sahara Desert on a moonless night, then observe the desert from an aircraft at 10,000 meters altitude. How many candles can you see? The answer depends on factors that have nothing to do with the number of candles. It depends on the direction you are looking at any given moment. It depends on whether clouds obscure portions of the desert. It depends on whether any particular candle happens to be burning at the exact moment your gaze passes over its location. It depends on whether the candle flame produces light in a wavelength your instruments can detect. A desert containing 1,000 candles might reveal 2 or 15 or none at all, depending entirely on observational geometry and instrument sensitivity, not on the actual count of flames. This is precisely the situation facing every SETI observation ever conducted. The galaxy might contain thousands of broadcasting civilizations, but the fraction of their signals that are physically capable of reaching us right now, aimed in our direction, in a frequency we are monitoring at a power level instruments can distinguish from background noise during the specific years we happen to be looking, that fraction could be vanishingly small, independent of the total population. There are 3 distinct reasons why a civilization that genuinely exists could be completely undetectable to us, and they are worth examining separately because each one closes off a different avenue of optimism. The first is transit time. As the previous section established a civilization whose signal bubble has not yet physically reached, our solar system is invisible to us by pure geometry. No technology, no sensitivity, no amount of observational patience changes this. The light simply has not arrived. The second is signal passage. A civilization might have been broadcasting powerfully and clearly for thousands of years. Its signal sphere might have already passed through our solar system, and we would have no record of it because we were not listening. Homo sapiens, as a species, is roughly 300,000 years old. Systematic radio telescope observation has been conducted for less than 1 century. If a civilization's detectable signal passed through our location between 200,000 years ago and 100 years ago, it is gone. It will not return. We missed it the way a person misses a train they did not know was coming. The third reason is the most philosophically confronting. A civilization might be broadcasting constantly. Its signals might be arriving at Earth right now, and we might be failing to recognize them as artificial because they use a communication method so different from radio that our instruments cannot distinguish their transmissions from natural background phenomena. Humanity is currently searching for signals that look like what humanity would send. This is not a criticism, it is the only rational starting point given our current knowledge. But it encodes a bias that is worth naming explicitly. A civilization 10,000 years more advanced than ours has had 10,000 years longer to develop communication technologies beyond radio. 10,000 years ago, humanity was in the early Neolithic period, working with polished stone tools and beginning to experiment with agriculture. The distance between that level of technological development and the construction of radio telescopes is the same temporal gap that separates us from a civilization that began advancing when we were still sharpening flint. What that civilization would use to communicate across interstellar distances, we genuinely cannot predict. Modulated gravitational waves, quantum entanglement-based encoding, directed neutrino beams, or methods that require physical principles not yet incorporated into human physics. Any of these is more plausible as their communication medium than radio, and none of them are what current SETI instruments are designed to detect. The deepest problem with the search for extraterrestrial intelligence is not resources or telescope sensitivity or funding, it is cognitive. Humanity is searching for an extraterrestrial version of itself, a species that happened to develop radio technology at roughly the same stage of civilizational development, happened to keep using it long enough for signals to reach us, and happened to point those signals in our direction. The absence of that very specific profile in our observations is being interpreted as cosmic silence, but it is more accurately described as the absence of one extremely narrow signal type from one extremely narrow detection window. The universe is not necessarily silent. It may simply be speaking in frequencies we have not yet learned to hear. If a civilization that arose 1 million years before our own has had 1 million years to advance beyond every technology, humanity currently understands what physical trace would they leave that we would actually be capable of recognizing as artificial rather than natural. That question leads directly into a hypothesis, generating fierce disagreement across the astronomical community right now, and it involves stars that are behaving in ways that current astrophysics cannot cleanly explain. In 2015, a paper published in the monthly notices of the Royal Astronomical Society drew the attention of astronomers in a way that few observational reports managed to do. It described a star catalogued as KIC 8462852, located approximately 1,470 light-years from Earth in the constellation Cygnus. The star had been observed continuously by NASA's Kepler Space Telescope between 2009 and 2013, and the data it produced was, by the measured standards of astrophysics, deeply strange. Stars dim when objects pass in front of them. This is the foundational principle behind the transit method of exoplanet detection, and it works with remarkable reliability. When a planet crosses the face of its host star, as seen from Earth, it blocks a small fraction of the star's light. The amount of dimming depends on the planet's size relative to the star. Jupiter, the largest planet in our solar system, would cause our Sun to dim by approximately 1% if it transited across its face as viewed from a distant observer. Earth would produce a dimming of roughly 0.01%, essentially undetectable without very sensitive instruments. KIC 846285, dimmed by 22%, 22%. Not once, but repeatedly at irregular intervals, with no discernible periodicity and with a light curve shape, the precise profile of how brightness dropped and recovered that did not match any known natural transit pattern. A planet large enough to block 22% of a star's light would need to be roughly half the diameter of the star itself. No planet of that size could exist in a stable orbit at the distances implied by the transit timing. The geometry simply does not work. To understand the scale of the anomaly in concrete terms, a standard planet transit produces a clean, symmetrical dip in brightness. The light curve drops smoothly as the planet moves in front of the star reaches a flat minimum, while the planet is fully transiting and recovers symmetrically as the planet moves away. What Kepler recorded from KIC 84622852 was irregular, asymmetric, and variable in depth across different events. Some dips were shallow and brief, others were deep and prolonged. Some showed complex internal structure suggesting multiple overlapping objects of different sizes moving across the star's face simultaneously. The pattern looked less like a planet and more like something assembled from many irregular components. Astronomer Tabitha Boyajian, who led the initial analysis of the data, openly acknowledged that the natural explanations were all problematic. A swarm of comets in an unusually tight formation was proposed as a possible cause, but detailed modelling of how such a swarm would need to be structured to produce the observed light curves revealed requirements that pushed the boundaries of what cometary dynamics could realistically deliver. Circumstellar dust clouds were considered, but dust clouds of the geometry needed to produce asymmetric dips of that magnitude would themselves need to be explained, and the dust dispersal models did not match the observed infrared signature of the star. Several scientists, including astronomer Jason Wright at Pennsylvania State University, formally proposed in published literature that the data was consistent with, though not proven to be a large-scale artificial structure in partial stages of construction around the star. Not a completed Dyson sphere, but something intermediate, a civilization in the process of building mega-scale infrastructure that had not yet achieved full coverage. The proposal was not sensationalism. It was a legitimate hypothesis offered in scientific context, with the appropriate caveats precisely because the natural alternatives were all unsatisfying. Subsequent observations added another layer of complexity. Long-term photometric records stretching back over a century, compiled from historical astronomical archives, suggested that KIC 8462852 had been gradually dimming in overall brightness over decades, a secular, fading trend separate from the sharp transit events, which, again, had no clean, natural explanation. More recent infrared data has pointed toward fine dust as the most probable culprit for the fading, which partially addresses the long-term dimming but does not fully resolve the irregular transit events in a way that satisfies all the data simultaneously. And then there is EPIC 249706694, a star identified in Kepler's extended mission dataset that showed dimming patterns with some structural similarities to KIC 8462852 though, less extreme in amplitude. Beyond that specific case, statistical analyses of the full Kepler catalogue have identified a small but non-zero population of stars exhibiting transit anomalies that resist clean classification under standard planetary or stellar models. The exact count depends on the detection threshold applied, but the pattern suggests that KIC 8462852 is unusual in degree rather than unique in kind. Two possibilities emerge from this body of evidence, and both of them are significant regardless of which turns out to be correct. The first possibility is that astrophysics contains gaps in its understanding of stellar environments, dust configurations, cometary dynamics, or circumstellar disk behavior that can produce anomalous photometric signatures not currently captured in standard models. If this is correct, it means the field has important unfinished work to do in characterizing natural stellar variability. That alone is a meaningful scientific finding. The second possibility is that some fraction of these anomalous signals reflect the presence of non-natural structures, not necessarily inhabited ones, not necessarily currently active ones, but structures built at some point by something with the engineering capacity to place objects the size of planets into coordinated orbits around a star. If this is correct, the implications extend far beyond astronomy. Neither possibility has been conclusively ruled out. What makes KIC 8462852 particularly important in the context of this discussion is not just the anomaly itself, but what the distance forces us to confront. The light currently reaching our telescopes from that star left its source 1,470 years ago. The year that light departed, the Tang dynasty was consolidating power in China. The Prophet Muhammad had recently unified the Arabian Peninsula. The Byzantine Empire still controlled Constantinople. Whatever is happening around that star right now, whether it is dust, dispersing a natural structure, evolving, or something being built, we will not receive updated information about it until the year 3495. If those structures are artificial, and if the civilization that built them still exists in any form, they have had 1,470 years of development since the light we are analyzing left their system. 1,470 years ago, humanity was operating at a level of technology that would be unrecognizable to a modern engineer. The gap between medieval metallurgy and a Kepler space telescope represents roughly 14 centuries of progress. Whatever that civilization has accomplished in the equivalent span of time is not something current human frameworks can meaningfully estimate. Any signal sent toward KIC 8462852 today would arrive in the year 3495. A response, if one came, would reach Earth around the year 4965. The civilization exchanging those messages would share nothing in common with the ones initiating the conversation. If those structures are artificial, and the civilization that built them has continued developing for 1,470 years since the light we are currently observing left their star, in what ways would they have advanced? And what would that level of advancement actually look like measured against anything humanity currently understands? Answering that question requires understanding a framework that physicists use to classify civilizations by the scale of energy they control. And the steps on that scale make the gap between humanity and a truly advanced civilization larger than the gap between an ant navigating a garden and an astronaut navigating the solar system. In 1964, Soviet astronomer Nikolai Kardashev was working on a theoretical framework for classifying the technological sophistication of civilizations when he arrived at a field of astrobiology and SETI research ever since. The insight was deceptively simple. The most reliable and universal measure of a civilization's advancement is not its philosophy, its culture, its political complexity, or even the sophistication of its tools. It is the total amount of energy that civilization can harness, direct, and deploy. Energy is the common currency of physics. Every technological capability, from the most primitive to the most advanced imaginable, ultimately reduces to the ability to move energy from one place to another in a controlled and purposeful way. A civilization that controls more energy can do more things, build larger structures, communicate across greater distances, and resist the entropic forces that would otherwise dismantle any ordered system. Energy mastery is, in the deepest physical sense, the definition of technological power. Kardashev proposed 3 benchmark levels. A Type 1 civilization harnesses all the energy available on its home planet, the full output of sunlight striking the surface, all geothermal energy from the planet's interior, all chemical and nuclear energy accessible from the planet's resources. A Type 2 civilization captures and utilizes the entire energy output of its host star, not just the fraction that happens to strike one planet, but the complete radiative output flowing outward in every direction through space. A Type 3 civilization commands the energy of an entire galaxy across hundreds of billions of stars simultaneously. These categories sound abstract until the actual numbers are inserted. The Sun releases energy at a rate of approximately 3.8 times 10 to the power of 26 watts continuously. Earth's total energy consumption across all human civilization, every power plant, every vehicle, every industrial process, every light switched on anywhere on the planet, currently runs at roughly 2 times 10 to the power of 13 watts. The ratio of those two numbers is roughly 20 trillion to 1. A Type 2 civilization commands 20 trillion times more energy than all of humanity uses today. And a Type 3 civilization commands approximately 10 billion times more energy than a Type 2. Physicist Michio Kaku, building on Kardashev's original framework, estimated that humanity's current position on this scale sits at approximately Type 0.73, not Type 1, not even close to Type 1, 0.73, a civilization that has not yet achieved full mastery of its own planetary energy resources, let alone anything beyond. The distance between 0.73 and Type 1 requires increasing total energy production by roughly 100,000 times. That is not a marginal improvement. It is the difference between where humanity stands today and a civilization that has harnessed every joule of solar energy, reaching every square meter of Earth's surface, extracted every accessible unit of geothermal heat from the planet's interior, and converted every available chemical, energy source into usable power. From Type 1 to Type 2, capturing the full output of an entire star requires multiplying energy capacity by approximately 10 billion times beyond that. The scale of these gaps resists any comfortable analogy, but consider the following. If the energy output of a Type 0 civilization is represented by a single lit match, then Type 1 is a forest fire consuming an entire continent. Type 2 is the Sun itself burning at the center of the solar system. And Type 3 is every star in the Milky Way ignited simultaneously and placed under coordinated control. Humanity is the match. There is something almost comic about the contrast between human self-perception and this physical reality. The Apollo program landing human beings on the surface of the moon and returning them safely to Earth remains one of the most celebrated achievements in the history of our species. It required the coordinated effort of 400,000 engineers, scientists, and technicians, consumed billions of dollars in resources, and demonstrated genuine mastery of orbital mechanics, materials, science, and life support. Engineering. On the Kardashev scale, this accomplishment is equivalent to an ant climbing to the top of a blade of grass and declaring that it has conquered the savannah. The ant genuinely climbed. The achievement is real. But the gap between that blade of grass and the savannah is not a matter of degree, it is a matter of category. The reason this scale matters for the question of cosmic silence is direct and unavoidable. A Type 3 civilization, by definition, is manipulating energy at the scale of an entire galaxy. The waste heat alone from that level of energy processing would produce a detectable infrared signature visible across intergalactic distances. The gravitational effects of relocating stellar mass objects would perturb the orbits of neighboring stars in measurable ways. The electromagnetic output of coordinated stellar engineering would create anomalies in spectroscopic surveys that no natural process could replicate. A Type 3 civilization cannot hide its existence through any passive means. Its operations would be written across the observable universe in signatures that even a Type 0 civilization with radio telescopes should be capable of. Detecting, and yet infrared surveys of the Milky Way and nearby galaxies have found no such signatures. The Glimpse survey, the WISE All-Sky survey, and multiple dedicated searches for anomalous stellar infrared excess, consistent with Dyson sphere construction, have found candidate objects that require further investigation, but no confirmed cases of galaxy-scale energy harvesting. The galaxy looks to every instrument pointed at it like a collection of natural stellar processes operating without coordinated intervention. This absence is not trivial. It either means Type 3 civilizations do not exist anywhere in the observable vicinity, or it means something about the assumption that advanced civilizations inevitably scale their energy use outward in ways that produce detectable waste heat. Both possibilities are deeply significant. If a Type 3 civilization controlling the energy output of an entire galaxy genuinely existed within the Milky Way, its infrared waste heat signature alone should be detectable from Earth using instruments we already possess. So why does every survey of our galaxy's infrared emission return results consistent with purely natural stellar processes? This is precisely the question a Russian physicist posed in 1964, and the answer he began constructing became one of the most unsettling ideas in the history of scientific thought. The Kardashev scale creates a problem. If advanced civilizations exist and inevitably scale their energy use to stellar or galactic levels, they should be detectable. They are not detectably present, at least not in any confirmed way. This gap between expectation and observation demands an explanation, and the explanations on offer divide roughly into two categories. Either advanced civilizations are genuinely absent, or they are present but deliberately concealing themselves. The second category leads to one of the most philosophically disturbing frameworks ever applied to the question of extraterrestrial intelligence. The core argument, developed independently by multiple thinkers and explored in rigorous detail by Chinese physicist and science fiction author Liu Cixin in his widely read work, proceeds from first principles of resource competition, decision theory, rather than from any assumption about alien psychology or morality. It requires no malevolence. It requires no aggression as a cultural trait. It requires only two axioms that are difficult to argue against, given the physical structure of the universe. The first axiom is that survival is the primary drive of any civilization that has persisted long enough to become technologically significant. This is not a claim about values or ethics. It is an observation about selection. Any civilization that did not prioritize its own continued existence would by definition tend not to continue existing. Over sufficient time, the civilizations that remain are the ones that have successfully navigated threats to their survival, which means they are the ones that took survival seriously. The second axiom is that usable resources in the universe are finite and non-replenishable on civilizational timescales. Stars have finite fuel. Accessible matter in any given region of space is limited. The energy budget of a galaxy, while vast by human standards, is not infinite, and a civilization consuming energy at Type 3 scale is drawing from a pool that can be depleted in principle. When two civilizations both require resources from the same finite pool, competition becomes structurally possible regardless of their respective intentions. From these two axioms, a logical chain unfolds with uncomfortable precision. When Civilization A detects the existence of Civilization B, it faces a fundamental uncertainty. It cannot verify B's intentions. B might be cooperative, peaceful, and entirely uninterested in conflict. But B might also be competitive expansionist, or simply operating under survival pressures that make conflict with A rational from B's perspective. Crucially, A cannot know which is true. Communication takes years or millennia across interstellar distances, making real-time negotiation impossible. There is no interstellar law enforcement. There is no mutual defense treaty that can be enforced across light years. There is no mechanism by which A can verify B's stated intentions with confidence sufficient to stake A's continued existence on. Given this irreducible uncertainty, the game theory of the situation produces a stark result. If A allows B to continue developing, and B turns out to be hostile, A faces potential destruction. If A eliminates B preemptively, and B turns out to have been peaceful, A has committed an unnecessary act but has survived. The asymmetry between these outcomes, extinction versus regret, creates a rational basis for preemptive action that does not require hatred, fear, or moral failure. It requires only the cold logic of survival under uncertainty. The conclusion is that any sufficiently intelligent civilization reasoning through this framework arrives at the same behavioral strategy: silence and concealment. Broadcasting your existence is functionally equivalent to illuminating yourself in a dark forest where predators may be present. The rational response is to move quietly, emit no detectable signals, and eliminate any source of light that might attract attention before it attracts the wrong kind. If this reasoning is valid, the galaxy is not empty. It is full of civilizations actively suppressing their own detectability, each one aware that revealing itself is a gamble whose downside is extinction and whose upside is contact with a civilization that might be friendly but cannot be verified as such. The silence of the universe under this framework is not the silence of an empty room. It is the silence of a forest where every creature has learned through evolutionary or civilizational experience that making noise is how you get eaten. There is a serious and important counterargument that deserves honest engagement. The dark forest hypothesis assumes that competitive zero-sum resource logic is universal, that any civilization reasoning clearly about survival will inevitably arrive at the same predatory calculus. But this assumption may itself be a form of cognitive projection. Human civilization has a specific evolutionary history, rooted in competitive survival on a single resource-limited planet. The assumption that this particular psychological orientation scales universally to all possible forms of intelligence across all possible environments may say more about human cognition than about the actual distribution of motivational structures in the cosmos. A civilization that evolved in an environment of genuine resource abundance, or one that developed cooperative survival strategies as its primary adaptive mechanism, or one that achieved a level of intelligence at which zero-sum resource competition became genuinely irrelevant to its needs, might reach entirely different conclusions from the same two axioms. The logic of the dark forest is airtight given its premises. The question is whether the premises are universal. But here is the unsettling thing about this counterargument. It does not actually make the situation safer. If the dark forest hypothesis is wrong, and most civilizations are not predatory, then the silence still requires a different explanation. And if even a small fraction of civilizations do operate on dark forest logic, even 1%, even 1 in a million, then the calculus for any broadcasting civilization becomes extremely uncomfortable. The risk is not symmetrical. You cannot be partially detected. Humanity has been broadcasting electromagnetic signals for approximately 120 years. That bubble of radio emission is expanding outward at the speed of light, currently reaching roughly 120 light-years in every direction. Whether this constitutes a dangerous level of exposure depends entirely on what, if anything, is listening within that radius, and whether the dark forest framework describes their decision-making. If the dark forest hypothesis is correct, and the electromagnetic bubble humanity has been generating for 120 years has already reached civilizations, operating on survival-first logic is the absence of any response so far actually reassuring, or does it simply mean the response has not arrived yet? That question is no longer confined to theoretical discussion. There is an active, unresolved, and genuinely contentious debate within the scientific community about whether humanity should continue transmitting signals into space at all, and the two sides are making arguments so compelling in opposite directions that no consensus has emerged despite decades of conversation. In 1998, economist Robin Hanson published a paper that reframed the Fermi paradox in a way that has never quite let go of anyone who genuinely thinks it through. The paper's central argument was not about alien psychology, not about communication technology, not about the speed of light. It was about probability and the structure of evolutionary history. And its most disturbing implication is not about what might be waiting for humanity in the future. It is about what the discovery of life elsewhere in the solar system would mean for humanity right now. The argument begins with a straightforward observation. The universe is very old. Stars capable of supporting life have existed for billions of years, and the physical and chemical ingredients for biology appear to be common throughout the cosmos. If the emergence of technologically advanced civilizations were a reasonably probable outcome of these ingredients, the galaxy should be populated with them. It is not, or at least it shows no detectable signs of being so. Something therefore must be making the path from inert chemistry to galaxy-spanning civilization extraordinarily difficult to traverse. Something acts as a filter, preventing almost every starting point from reaching the finish line. Hansen called this obstruction the Great Filter. It does not need to be a single event or a single barrier. It could be a series of steps, each improbable enough to eliminate most candidates whose combined improbability produces an effective wall between the abundance of potentially life-bearing planets and the scarcity of detectable civilizations. The filter is real in the sense that something must explain the gap between expectation and observation. The question that determines everything is where in the sequence of steps from chemistry to civilization that filter is located. Two possibilities exist, and they lead to conclusions that could not be more different in their implications for humanity. The first possibility is that the filter lies behind us. One or more steps in the long chain from simple chemistry to technological civilization, the first self-replicating molecule, the emergence of the eukaryotic cell with its membrane-bound nucleus, the transition from single-celled to multicellular organisms, the development of complex nervous systems, the appearance of symbolic language and cumulative culture. One of these transitions was so improbable that it almost never occurs. Most planets with the right chemistry never produce life. Most planets with simple life never produce complex multicellular organisms. Most planets with complex life never produce intelligence. Whatever the bottleneck was, humanity passed through it somewhere in its 4 billion-year biological history, and the vast majority of other planets did not. If this is correct, the implication is sobering but not catastrophic. Humanity is extraordinarily rare, possibly unique in the observable galaxy, a statistical miracle produced by a chain of improbable events that almost certainly did not replicate themselves at any other location within detectable range. The silence of the universe is the silence of near-total biological failure everywhere except here. Humanity is alone not because civilization is impossible, but because the particular sequence of biological accidents that produced intelligence happened to us and essentially no one else. The second possibility is that the filter lies ahead. Every step from chemistry to technological civilization is actually fairly probable. Simple life emerges readily wherever conditions permit. Multicellular life complex, nervous systems, intelligence, language, technology. These transitions while not trivial, are common enough that the galaxy should be filling up with civilizations. But something terminates technologically advanced civilizations before they become detectable and persistent on galactic timescales. Something destroys or suppresses intelligent species at some point after they develop radio telescopes and before they develop the capacity for interstellar colonization. The filter is not in the past. It is waiting in the future of every civilization that reaches our current stage of development. The candidates for a forward filter are not difficult to identify. Full-scale nuclear exchange remains possible, as long as large arsenals exist and political systems remain capable of catastrophic miscalculation. Artificial intelligence developing in ways that misalign with the interests of its creators is an increasingly discussed risk as computational capabilities expand. Engineered biological agents, capable of pandemic-scale lethality, represent a threat that grows as biotechnology becomes more accessible. Irreversible alteration of planetary climate systems could render technological civilization unsustainable before the engineering solutions to reverse that alteration are developed. And there may be failure modes that no civilization at our level of development has yet encountered or conceived, risks that only become apparent after crossing thresholds of technological capability we have not yet reached. What makes this framework particularly compelling is the observation that the laws of physics, chemistry, and evolutionary biology are the same everywhere in the universe. If biology on Earth followed a particular developmental sequence constrained by thermodynamics and natural selection, then biology elsewhere emerging under similar constraints would tend to follow similar paths. If technological civilizations on Earth face particular existential risks arising from the specific dynamics of rapid technological development, the gap between the ability to create destructive capabilities and the institutional wisdom to manage them, then technological civilizations elsewhere would tend to face structurally similar risks at structurally similar stages. The filter, whatever it is, may be universal precisely because the universe applies the same rules everywhere. Now comes the part that most discussions of this topic handle too gently. The discovery of life elsewhere in the solar system, not intelligent life, not technological civilization, but simple microbial life. Even fossilized evidence of past microbial life on Mars or in the subsurface ocean of Enceladus would be among the most consequential scientific findings in human history. And depending on your position on the Great Filter, it would also be among the most alarming. Here is why. If life is found on Mars, it means that life can emerge independently on at least two separate bodies within the same solar system. This dramatically increases the estimated probability that life emerges wherever conditions are broadly suitable. If life emerges readily, then the filter is not in the early steps of biology. It is not in the improbable chemistry of the first self-replicating molecule. It is not in the transition from simple to complex cellular structures. All of those steps, if life arose independently on Mars, are merely difficult rather than nearly impossible. The filter that explains the silence of the galaxy, therefore, cannot be behind us. It must be ahead. Finding bacteria on Mars might be the worst news humanity ever receives, not because the bacteria are dangerous, but because their existence would be strong evidence that the Great Filter is something no civilization has yet survived, that we are approaching it. The sterile alternative, absolute confirmation that Mars has never hosted any form of life despite having had liquid water, organic chemistry, and a stable atmosphere for hundreds of millions of years in its early history, would actually be reassuring by comparison. It would suggest that the origin of life itself is the filter, that the step from chemistry to biology is so improbable that even favorable conditions usually fail to produce it, and that humanity's existence represents the successful, the navigation of the hardest transition in the entire sequence. The filter would be behind us, not ahead. If forced to choose between these two discoveries, microbial life confirmed alive on Mars today, or absolute sterility confirmed across every potentially habitable body in the solar system, which finding should humanity genuinely hope for, and why does the answer feel so counterintuitive? That question is not purely philosophical. It connects directly to how astronomers calculate the long-term survival probability of our species, and a specific figure has emerged from those calculations that reframes everything about how seriously to take the risks ahead. The The Milky Way is approximately 13.6 billion years old. The solar system, by contrast, is 4.6 billion years old. The arithmetic of that difference is worth sitting with for a moment, because it contains an implication that most discussions of extraterrestrial life entirely skip over. There are stars in the Milky Way that formed 9 billion years before our Sun existed. Not 9 billion years older than Earth. 9 billion years older than the Sun itself, which means 9 billion years before the planetary disk from which Earth eventually condensed had even begun to accumulate. These are ancient stars, many of them now in the late stages of their stellar evolution, some already collapsed into white dwarfs or neutron stars. But billions of years ago, when they were in their stable main sequence phase, providing steady energy to whatever planetary systems formed around them, the conditions for biology may have been present. If life emerges with any consistency, wherever liquid water, organic chemistry, and stable energy exist, and these are the conditions that produced life on Earth, then civilizations could have arisen around some of these ancient stars billions of years before our solar system formed, not millions of years before. Billions. To grasp what 9 billion years of additional development time actually means, consider the following compression. If the full age of the Milky Way were collapsed into a single 24-hour day, our Sun would not ignite until approximately 8 hours before midnight. Anatomically, modern humans would appear in the final fraction of the final second before midnight. But a civilization that arose around a 9 billion year older star would have appeared before noon, before the halfway point of the galactic day, and would have had the entire afternoon, evening, and most of the night to develop, expand, transform, and either persist or collapse before our solar system produced its first rocky planets. 9 billion years ago, Earth did not exist. The atoms that now compose every human body were still dispersed through interstellar gas clouds, unassembled, unstructured part of no planet and no biology. Any civilization that arose in the early galaxy would have run its entire civilizational arc, from first tools to whatever its ultimate form became, while the matter of Earth was drifting through space, waiting to be gravitationally assembled. The consequences of this timeline for the search for extraterrestrial intelligence are profound and largely underappreciated. If such civilizations existed, they would have had incomprehensibly more time to develop than humanity has. They would have reached whatever their equivalent of the Kardashev scale milestones were confronted, whatever their version of existential risks looked like, and either navigated past those risks or failed to do so, all of it completed, and resolved billions of years before our planet formed. Their history would be finished. Whatever they built, whatever they became, whatever traces they left, all of it would have been subject to 9 billion years of cosmic weathering, stellar evolution, radiation bombardment, and entropy before humanity developed instruments capable of searching for it. Stars age and change. A civilization orbiting a star that subsequently exhausted its fuel and swelled into a red giant would have faced the destruction of its home system on astronomical timescales, regardless of its technological sophistication. The records of their existence, physical structures, engineered megaprojects, modified stellar environments would have been engulfed, irradiated, or dispersed long before our telescopes existed to look for them. The universe does not preserve archaeological sites across billions of years. Entropy and stellar evolution erase them. This introduces a dimension to the search for intelligence that the standard formulation of the Fermi paradox does not adequately incorporate. The question is not only whether other civilizations exist somewhere in the galaxy at this moment, it is whether any two civilizations that exist or have existed are separated by a temporal gap small enough to allow meaningful overlap. Two civilizations that are each technologically advanced for 1 million years, but whose million-year windows are separated by 5 billion years of galactic time, will never interact regardless of their respective capabilities or intentions. They missed each other by an interval longer than the entire history of complex life on Earth. The real search, properly framed, is not a search across space alone. It is a search across space and time simultaneously. A civilization must exist, must be located within a manageable distance, must be at a technological stage where it produces detectable signals, and must be doing all of this at the same cosmic moment that we are looking. The conjunction of all four conditions, existence, proximity, detectability, and simultaneity, may be far rarer than any single one of them alone. The window of temporal overlap is the overlooked variable in almost every popular discussion of the Fermi paradox. Civilizations are not permanent features of the cosmos. They are temporary flickers of organized complexity, each one burning for some finite duration against a background of deep time that dwarfs them entirely. The probability of two such flickers overlapping in both space and time, closely enough and at the right stage to exchange any signal, may be the smallest number in the entire Drake equation, smaller even than the probability of intelligence arising in the first place. If the probability of two civilizations existing simultaneously within signal range of each other is lower than the probability of two signal bubbles, physically overlapping, does the universe function at its deepest structural level as a place where civilizations are almost always alone, not because they are rare, but because they perpetually arrive at wrong times relative to each other. That question about timing leads directly to a recent discovery that is forcing astronomers to fundamentally revise their models of where and when life is most likely to exist, and it centers on the type of star that makes up nearly 3/4 of the entire stellar population of the galaxy. Every search image humanity has constructed for a potentially habitable world looks in some fundamental way like a modified version of Earth. A rocky planet, liquid water on the surface, an atmosphere with the right chemistry, a comfortable distance from its host star, and crucially, almost always implicitly, a star that resembles our Sun, a yellow-white main sequence star of moderate size, moderate temperature, and moderate luminosity. This is an understandable starting point. Earth is the only example of a life-bearing world we have ever confirmed, and the Sun is the only star we know has successfully sustained a biosphere for billions of years. Searching for Earth-like planets around Sun-like stars is not irrational. It is the most conservative, evidence-grounded approach available. It is also, by the cold arithmetic of stellar demographics, a search focused on a minority of the galaxy. 73% of all stars in the Milky Way are red dwarfs. Not a plurality, not a slight majority. Nearly 3 out of every 4 stars in the entire galaxy belong to this category. Small, dim, cool, and so fundamentally different from our Sun that the planets orbiting them experience a completely alien stellar environment. Red dwarfs are sometimes called M-type stars in the spectral classification system, and they range from about half the mass of the Sun down to objects barely large enough to sustain hydrogen fusion at all. They shine with a fraction of the Sun's luminosity, emit most of their radiation toward the red and infrared end of the spectrum, and live for durations that make the Sun's 10 billion year lifespan look almost fleeting. The Sun will burn for approximately 10 billion years, in total of which roughly 4.6 billion have already elapsed. The smallest red dwarfs, those at the lower end of the mass range, will continue fusing hydrogen for approximately 10 trillion years. Not 10 billion, 10 trillion. That number is 1,000 times the current age of the universe itself. The universe has existed for 13.8 billion years, and the smallest red dwarf stars will still be burning steadily when the universe is 1,000 times older than it is today. The implications of this longevity for the question of life and intelligence are staggering in ways that have only recently begun to receive serious attention in the astrobiological community. On Earth, the journey from the first self-replicating chemistry to a technological civilization capable of building radio telescopes took approximately 4 billion years. That 4 billion year arc encompasses everything: the emergence of the first cells, the billion-year development of photosynthesis, the slow accumulation of atmospheric oxygen, the Cambrian explosion of complex animal body, plans, the colonization of land, the evolution of vertebrates, rise and extinction of the dinosaurs, the diversification of mammals, the emergence of primates, the development of human intelligence, language, agriculture, metallurgy, industry, and electronics. 4 billion years start to finish. A planet orbiting a small red dwarf star has access to a stellar energy source that will remain stable for 10 trillion years. If evolution on such a planet proceeds at a broadly similar pace to evolution on Earth, constrained by the same thermodynamic principles, the same chemistry of carbon-based molecular replication, the same selection, pressures of survival, and reproduction, than a civilization around a red dwarf has. Not 4 billion years to complete the journey from chemistry to intelligence, but 10 trillion. That is 2,500 times longer than it took life on Earth to traverse the entire distance from first chemistry to technological civilization. 2,500 iterations of 4 billion-year evolutionary histories available in sequence around a single stable star. The number is so large it initially seems meaningless, but consider what it actually implies. If a civilization around a red dwarf formed at roughly the same time, the galaxy's first red dwarf stabilized, which was many billions of years ago. And if that civilization survived and continued developing, it has had access to an evolutionary and technological runway of incomprehensible length. The question of what intelligence becomes after trillions of years of development is not one that current human frameworks are equipped to address, because the entire history of human thought fits inside a period shorter than the rounding error on that timeline. There is, of course, a significant complication. Planets in the habitable zone of a red dwarf, the region where liquid water could exist on the surface, orbit extremely close to their host star. For a dim, cool star, the habitable zone lies at a fraction of the distance between Earth and the Sunday. At such close orbital distances, a phenomenon called tidal locking becomes likely over geological timescales. Tidal locking occurs when a planet's rotation period synchronizes with its orbital period, resulting in one hemisphere permanently facing the star and the other permanently turned away. One side bakes in perpetual daylight, the other freezes in permanent night. For decades, this was considered a probable death sentence for habitability around red dwarfs. A planet with a permanent day side and a permanent night side would, the reasoning went, develop such extreme temperature differentials that no stable climate could emerge across the full planetary surface. More recent atmospheric modeling has substantially complicated this picture. Research published over the past decade suggests that a planet with a sufficiently thick atmosphere could redistribute heat from the day side to the night side through circulation patterns, moderating the temperature differential enough to maintain liquid water across much of the surface. The terminator zone, the narrow band of perpetual twilight running along the boundary between the permanent day and night hemispheres, emerges in some models as an environment of remarkable thermal stability. Neither blasted by unfiltered stellar radiation nor frozen in deep space cold, the terminator would experience conditions that are, in certain respects, more consistently moderate than anything found on Earth's surface, where day-night temperature swings and seasonal variation create constant environmental fluctuation. Whether life has actually developed around any red dwarf remains unknown. The observational challenges are formidable. Red dwarfs are prone to intense stellar flares, sudden releases of magnetic energy that can briefly increase the star's ultraviolet and X-ray output by factors of hundreds or thousands. These flares could strip away the atmospheres of close-orbiting planets or deliver lethal radiation doses to any surface biology that had not evolved robust protective mechanisms. Whether planetary magnetic fields and thick atmospheres can adequately shield surface life from this flare activity is an active research question without a definitive answer. But here is the dimension of this that deserves explicit acknowledgement, because it almost never comes up in discussions of the search for extraterrestrial intelligence. Humanity has spent enormous resources, billions of dollars in telescope, time, satellite missions, and research programs searching for Earth-like planets around Sun-like stars. This is a search focused on the 27% of the galaxy's stellar population that most resembles our own star, looking for planets most similar to Earth, hosted by stars whose lifetimes most resemble the Sun's. The search is methodologically reasonable. It is also, if red dwarf habitability turns out to be viable, a search that has been systematically overlooking the environments where the oldest, most developed potential civilizations in the galaxy would most likely be found. If life can persist around red dwarfs, and if civilizations have been developing around them since the early galaxy, then the most ancient intelligences in the Milky Way are not orbiting sun-like stars. They are orbiting the dim, cool, unremarkable red dwarfs that make up nearly 3/4 of the stellar population stars, so faint that many are invisible to the naked eye, despite being closer to Earth than some of the bright stars in the night sky. The search has been looking at the younger, rarer stars. The ancient ones have been hiding in plain statistical sight all along. If a civilization has been evolving around a stable red dwarf star for 1 trillion years, a duration 100 times longer than the current age of the universe, would the concept of civilization as humanity understands it, with its structures, communications, and physical infrastructure, bear any meaningful resemblance to what that entity has become? That question touches the final boundary, not the boundary of space, but the boundary of comprehension, and it explains why the silence of the universe may never be broken, even if intelligence fills every corner of it. Every model of advanced extraterrestrial civilization that has shaped the popular imagination shares a fundamental assumption so deeply embedded that it almost never gets identified as an assumption at all. The assumption is that more advanced means larger, that the trajectory of civilizational development points outward toward more planets, more stars, more physical territory, claimed more megastructures built, more signals broadcast across ever greater distances. The image of a truly advanced civilization is an empire, vast, expansive, visible, loud. This assumption is intuitive because it describes the arc of human history with reasonable accuracy. From bands of hunter-gatherers to agricultural settlements to city-states to empires to nation-states to a globally connected industrial civilization, the trajectory of human development has been one of increasing physical scale, increasing territorial reach, and increasing energy consumption. It seems natural to extrapolate this trend forward, to imagine that a civilization a million years more advanced than humanity would simply be a much larger, much more energetic version of what we are now. But there is a competing hypothesis developed seriously within the academic literature on the Fermi paradox that suggests this extrapolation breaks down at a certain level of technological sophistication. The hypothesis is called the transcension hypothesis, and its central claim is that the most advanced civilizations do not expand outward into macro-scale space. They expand inward into the micro-scale structure of matter and information. The physical reasoning behind this claim is grounded in the fundamental principles of computation and information theory. The efficiency of computation, the amount of useful processing, achievable per unit of energy, consumed scales favorably with physical miniaturization. Smaller computational elements switch faster because electrical signals traverse shorter distances. Denser packing of information storage allows more data to be accessed in less time. Heat dissipation, which is the primary limiting factor in all computation, is managed more effectively at smaller physical scales, where the surface area to volume ratio is more favorable. A civilization whose primary activity is the processing and manipulation of information, which is what any sufficiently advanced civilization would arguably become, since information processing underlies every form of engineering science. Communication and cultural activity would find that shrinking. Its physical footprint, rather than expanding it, yields compounding efficiency gains. The most powerful computer achievable is not a planet-sized machine. It is the densest, most efficiently organized information processing structure physically permitted by the laws of quantum mechanics and thermodynamics, operating at the smallest scale those laws allow. The logical endpoint of this trajectory is a civilization that has compressed its entire existence, its population, its culture, its ongoing activities, its accumulated knowledge into a volume of space that would be physically undetectable to any external observer searching at macro scales. Not a Dyson sphere around a star, not megastructures visible across light years. A structure the size of a dust grain or smaller, containing computational density and subjective richness that exceeds anything a civilization spreading across 1,000 star systems could achieve through outward expansion. This is not science fiction speculation. The theoretical basis for extreme miniaturization of computation is grounded in real physics. The Bekenstein bound derived from the work of physicist Jacob Bekenstein on black hole thermodynamics establishes a theoretical maximum for the amount of information that can be encoded within a given region of space with a given amount of energy. The numbers this bound produces suggest that the information processing capacity of matter at its physical limits vastly exceeds anything that macro-scale engineering could access. A civilization that learned to approach the Bekenstein limit in its computational architecture would effectively become invisible to any observer looking for city-sized structures, stellar megaprojects, or galaxy-spanning energy. Signatures. The absence of detectable megastructures is under this framework not evidence that advanced civilizations do not exist. It is evidence that they advanced past the phase where megastructure construction was the most efficient use of their capabilities. They shrank. They went deep rather than wide, and in doing so they vanished from the observable universe, not through destruction, but through a form of technological transcendence that rendered macro-scale space irrelevant to their purposes. There is something profoundly disorienting about this possibility, because it inverts every intuition humanity has built up about what progress means. The entire history of human technological development points toward greater reach, greater scale, greater visibility. The pyramids were larger than the mud huts that preceded them. Cathedrals were larger than temples. Cities are larger than villages. Industrial infrastructure covers continents. The assumption that advancement means growth in physical scale is baked into human cognitive architecture at a level that feels like common sense rather than assumption. But the physics of computation does not care about human intuitions. If the optimal configuration for a maximally capable information processing system is a dense, compact, nearly invisible structure operating at quantum mechanical scales, then the most advanced civilization achievable within the laws of this universe may be one that a telescope cannot find, that a radio receiver cannot hear, and that a physical probe would pass through without detecting, not because it is not there, but because it occupies a domain of physical reality that macro-scale instruments are not designed to probe. Humanity is currently searching for extraterrestrial civilizations by looking outward at stellar and galactic scales. Radio telescopes scan for electromagnetic signals in the radio and microwave bands. Optical instruments search for anomalous infrared signatures consistent with stellar energy harvesting. Photometric surveys catalogue unusual stellar dimming patterns that might indicate megastructure construction. Every instrument pointed at the sky is designed to detect the macro-scale signatures of a civilization that assumed the same developmental trajectory humanity is currently following. If the transcension hypothesis is correct, these searches are looking in the right direction, but at entirely the wrong scale. The advanced civilizations are not in the space between the stars. They are in the structure of matter itself, invisible to every instrument, designed to find them operating at a level of complexity and capability that renders the entire macro-scale universe, including the 100,000 light-year span of the Milky Way that so thoroughly defeats every proposal for galactic empire as irrelevant to their existence as the space between atoms is irrelevant to the functioning of a biological brain. The galaxy that appears empty to radio telescopes may not be empty at all. It may be full of minds that have simply stopped being the kind of thing that radio telescopes can detect. If the ultimate trajectory of civilizational development is inward rather than outward, compression rather than expansion, then what we interpret as an empty galaxy may in fact be a galaxy already filled beyond our capacity to measure, occupied by intelligences operating in domains of physical reality that our instruments by design cannot access. Does the apparent emptiness of the cosmos prove absence, or does it prove only the limits of our current ability to look? That question has no answer that current science can resolve, but the absence of an answer is itself the most important thing physics and cosmological philosophy can offer humanity about its place in the galaxy, and it changes everything about how to think about what comes next. Pull back from every specific argument examined across this story, the finite signal bubbles, the Drake equation's hidden assumptions, the anomalous stars, the Kardashev scale's humbling arithmetic, the dark forest's cold game, theory, the great filter's uncomfortable probability, the Zekle, temporal paradox of civilizations perpetually missing each other, the trillion-year lifespans of red dwarf stars, the transcension hypothesis's inward turn, and a single coherent picture assembles itself from all of these pieces. The universe is not silent because it is empty. It is silent because the physical laws that govern it make connection between independent islands of intelligence nearly impossible to achieve and almost certain never to last. Every civilization that has ever existed or ever will exist burns in its own corner of the cosmos. It generates light in the broadest sense, electromagnetic signals, gravitational perturbations, infrared waste heat, the chemical signatures of biology in a planetary atmosphere, the anomalous dimming of a star whose light is being partially intercepted by engineered structures. All of these are forms of light, leaking outward from the fire of an organized, energy-consuming intelligence. And all of them travel at the speed of light, which means they arrive at any distant observer, not as current information, but as a message from the past. Sometimes a recent past measured in years, sometimes a deep past measured in millions of years, depending on the distance involved. The ocean between any two fires is not merely wide, it is temporally distorting. Every civilization looking outward sees every other civilization not as it is, but as it was. The further away the fire, the older the light. A civilization 1,000 light years away is seen as it existed 1,000 years ago. A civilization 10,000 light years away is seen through a window 10,000 years into its past. Two fires burning simultaneously in the present moment of the cosmos are invisible to each other in any real-time sense. They can only exchange archaeological records messages from versions of themselves that no longer exist by the time the signal arrives. This is the most beautiful and most devastating paradox in all of cosmology. The same physical laws that make life possible are the laws that prevent life from connecting at scale. Carbon chemistry, the molecular flexibility of carbon bonds that allows the construction of proteins, nucleic acids, and the entire machinery of biology, works because of electromagnetic forces operating at quantum mechanical scales. Those same electromagnetic forces govern the behavior of light. The thermodynamics that drives metabolism, that converts chemical energy into the organized work of living systems, is the same thermodynamics that governs the dispersal of heat across space. The same thermodynamics that makes maintaining any ordered structure against entropy an energy-expensive enterprise. The fluid dynamics that shapes weather, ocean currents, and the circulation patterns that distribute heat across planetary surfaces. The same physics applied at different scales governs the dynamics of stellar nebulae and the structure of galaxy formation. The universe did not give life one set of laws and communication another. It gave everything the same laws, and those laws applied at the scale of a galaxy produce isolation as reliably as they produce complexity at the scale of a cell. Understanding this has a specific and underappreciated practical consequence for how humanity thinks about its situation. The twin anxieties that dominate popular discourse about extraterrestrial intelligence, the hope that advanced aliens will arrive to solve humanity's problems, and the fear that advanced aliens will arrive to destroy humanity, both rest on a shared assumption that physical interaction between civilizations separated by interstellar distances is a realistic near-term prospect. The physics examined throughout this account suggests that assumption is almost certainly wrong for reasons that have nothing to do with alien intentions and everything to do with the geometry of space and the finite speed of light. A civilization capable of crossing interstellar distances to reach Earth would need to have solved propulsion challenges that currently have no solution within. Known physics sustained the voyage across timescales that challenge the process, survival of any technological system, and chosen to target this particular unremarkable planet around this particular average star in this particular peripheral region of the galaxy. The probability of this conjunction of factors occurring within any timescale relevant to current human decision-making is low enough to be functionally negligible as a planning variable. Neither rescue nor invasion is coming. The nearest stars are years of light travel away at the absolute maximum speed permitted by the laws of physics, and nothing in those laws permits shortcuts. This is not a counsel of despair. It is a clarification of where the actual stakes lie. What it means in the most direct terms available is that humanity is conducting its experiment alone, not alone in the sense of being the only intelligence in the cosmos. The arguments assembled here suggest that is probably not true. Alone in the sense of being entirely responsible for its own outcome, without external intervention in either direction, for any timescale that matters to anyone currently alive or likely to be born within the next several centuries. Each civilization is in this framework, an independent experimental trial run by the universe on the question of what intelligence can become when given sufficient time, energy, and matter to work with. The universe does not specify what the answer should be. It does not reward particular outcomes or penalize others. It simply provides the ingredients, the physics, the chemistry, the astronomical environments, and runs the experiment simultaneously across billions of candidate locations, each one isolated from the others by distances that prevent the results of one trial from contaminating or rescuing any to other. Humanity is currently at Kardashev 0.73 in that experiment. The match has been lit. Whether it becomes a forest fire, a sun, or simply burns out after a brief bright interval is a question whose answer depends almost entirely on decisions made within the next few centuries, not the next few million years, not the next few thousand. The next few centuries, the period during which the gap between technological capability and institutional wisdom to manage that capability will determine whether humanity passes through whatever version of the Great Filter lies ahead. The civilizations that passed their filters, if any did, are not going to explain how they did it. The signal carrying that information has not arrived, will not arrive, and may never arrive. The civilizations that failed their filters left no useful record of what went wrong. Humanity is navigating this transition without a manual, without precedent it can actually access, and without any external authority capable of intervening. That is the actual situation. Not frightening alien empires, not benevolent cosmic mentors, just physics, chemistry, time, and the choices that an intelligent species at 0.73 on the Kardashev scale makes when it realizes through the accumulation of centuries of scientific observation that it is burning alone in a very large and very dark ocean. The darkness of that ocean does not imply that the fire should stop burning. It implies the opposite. If the fire goes out, it goes out permanently. The matter and energy that composed it disperses. The organized information encoded in its culture, its knowledge, its accumulated experience of navigating existence gone, not preserved, not inherited by anyone, not retrievable. Unlike a star that collapses and seeds, the interstellar medium with heavy elements that will become the next generation of planets, a civilization that ends, leaves almost nothing behind that serves the next attempt. It simply ends. The positive version of the Island of Fire framework is not comfortable in the way that stories about cosmic brotherhood and galactic federations are comfortable, but it has an integrity that the comfortable versions lack. It says, this fire, right here, burning on this specific planet, around this specific star, in this specific moment of cosmic time. This particular experiment in what intelligence can become is irreplaceable. Not because humanity is cosmically special in some mystical sense, but because it is here, it is running, and the physical structure of the universe guarantees that no other experiment will step in if this one ends. There are somewhere in the darkness other fires. They are burning in isolation, just as this one burns. They are conducting their own experiments in what intelligence and organization and culture can become when the laws of physics are given enough time to play out. Most of them are invisible to us. We are invisible to most of them. The ocean between us is too wide for light to cross in any interval that maps onto civilizational decision-making. We will never compare notes in real time. We will never coordinate. We will never rescue each other. But they burn, and the fact that they burn separated from us by distances that physics refuses to let us bridge means that intelligence is not a cosmic accident likely to be unique to one small planet. It is something the universe produces wherever the conditions allow in isolation, independently again and again, across deep time and vast space, each iteration unique, each one unreachable by the others, each one lighting its own small patch of an ocean that is by every measure that matters infinite. If humanity is the only technological civilization within 1,000 light-years in every direction, a sphere containing roughly 11 million stars, what does that imply about the responsibility carried by the specific choices made on this specific planet over the next century, given that no other intelligence within that entire volume can observe, influence, or inherit what happens here? The galaxy does not fall silent because it is empty. It falls silent because every fire burns far enough from every other fire that the light between them takes longer to cross than any civilization has existed, longer than any language has survived, longer than any institution has held. Each fire is alone in its darkness. Each one burns without knowing whether the darkness around it hides other fires or nothing at all. And each one, if it lasts long enough, if it builds instruments sensitive enough, if it asks the right questions of the faint signals, arriving from incomprehensible distances, eventually arrives at the same understanding that somewhere out, They're separated by an ocean no ship has ever crossed another. Intelligence is looking up at the same darkness and asking the same question and will never receive the answer and burns on regardless.